In the next two lectures, we're going to talk about what it really means when a covalent bond is formed. Specifically, we'll describe orbital overlap and hybridization in covalent molecules to explain the bonding and shape of a molecule in this first lecture. Then we'll discuss sigma and pi bonding in the second lecture. Let's begin. According to valence bond theory, a covalent bond forms from an overlap in the valence orbitals of the atoms involved. Let's look at the formation of a hydrogen-hydrogen single bond to illustrate the process. Starting at position A on the graph, we can examine the effect internuclear distance has on the potential energy of this two-atom system. Moving from A to C, as the hydrogen atoms approach each other closely, the potential energy decreases because of the attraction between the positive nuclei to the negative electrons on the other atom. Eventually, the potential energy reaches a minimum, which determines the bond length. If the two atoms got any closer, as in position D, the potential energy would increase due to repulsion of the positive nuclei coming too close to one another. The overlapping orbitals of the hydrogen atoms are each half-filled, initially with independent spins. Once the bond forms, both electrons occupy the area of the overlap and must be spin paired, which means that one of the electrons may have to reverse its spin so that one is spin up and the other is spin down. According to valence bond theory, the shape of a molecule is determined by the geometry of these overlapping orbitals. In its simplest form, valence bond theory works well for many diatomic molecules. For example, a hydrogen atom with a half-filled 1s orbital overlaps with a half-filled 3p orbital on the chlorine atom. The predicted result is a linear molecule with increased electron density along the internuclear axis, x, which I can draw in here as a straight line. Valence bond theory doesn't work as well once you increase the complexity of the molecule. For example, in water, an oxygen atom with two half-filled 2p orbitals overlaps with a half-filled 1s orbital on each hydrogen atom, giving bond angles of 90 degrees. We observe that bond angles in water are actually 105 degrees, which is slightly less than the predicted 109.5 degrees for a tetrahedral molecule containing 4 electron domains. They're all bonds and not lone pairs, which take up more space. So, how do we refine valence bond theory to fit our observations? Hybrid orbitals are mathematical combinations of atomic orbitals that result in the maximum overlap of orbitals in bonds. The number of hybrid orbitals will equal the number of atomic orbitals being combined. The shapes and energies of atomic orbitals being combined determines the shapes of the hybrid orbitals. We must recognize that atoms hybridize when bonding can't be avoided, and the energy cost of forming the hybrid orbitals is offset by the lower energy of the final molecule. Remember, the goal of all chemistry is to find the lowest energy state in which to reside. Let's look at the hybrid orbitals that are possible. In methane, CH4, we know carbon makes 4 equivalent single bonds with hydrogen atoms. To accomplish this, the 2s orbital hybridizes, or mixes with, all 3 2p orbitals on the carbon atom to form 4 identical sp3 hybrid orbitals, each half-filled with the same energy. Remember, orbitals with the same energy are called degenerate orbitals. These hybrid orbitals on the carbon overlap with the 1s orbitals on the 4 hydrogen atoms to form the tetrahedral molecule. It helps to think about how many electron domains will be on the central atom of the complete molecule. If we need 4 bonding domains made up of hybrid orbitals, then we have to add 1s orbital and enough p orbitals, 3 in total, to make the 4 hybrid orbitals, since we need 4 electron domains. Let's look at some examples. Here are 3 tetrahedral molecules that all contain sp3 hybrid orbitals. In our first example, the sp3 hybrid orbitals on carbon, in green, overlap with the 1s orbitals on each hydrogen. In tetrahedral electron geometries with lone pairs, the lone pair occupies one of these hybrid orbitals. We see this with one lone pair in ammonia, NH3, and with two lone pairs occupying the hybridized orbitals in water, H2O. In ethane, C2H4, each carbon atom bonds with three other atoms, two hydrogen atoms and one carbon atom. This requires a different type of hybrid orbital originating from the carbon atom, an sp2 hybrid orbital. This allows for three electron domains around each carbon because we use three atomic orbitals, s plus p plus p, to get three hybridized orbitals. Let's take a closer look. Each carbon atom combines its 2s orbital with two of its 2p orbitals to form three equivalent half-occupied sp2 hybrid orbitals with a trigonal-planar shape. This leaves one unhybridized p orbital that also plays an important role in bonding in this molecule, but we'll pick up that topic in the next lesson. In ethine, C2H2, the carbon atoms form bonds with two atoms, one hydrogen atom and the other carbon atom. This means we need two hybridized orbitals for the two electron domains around each carbon. We can get them by combining an s atomic orbital with a p atomic orbital. Let's take a closer look. Each carbon atom combines its 2s orbital with one of its 2p orbitals to form two equivalent half-occupied sp hybrid orbitals with a linear electronic geometry. The two unhybridized p orbitals are oriented at right angles to the internuclear x-axis and to each other. Let's summarize what we've learned so far. Our tetrahedral electronic geometry is made possible using four equivalent sp3 hybridized orbitals. A trigonal planar geometry, represented by three electron groups, is due to the presence of three sp2 hybridized orbitals, and a linear geometry is due to two sp hybridized orbitals. As always, I'll leave you with the parting thoughts of the authors. For now, it's only two review slides from this section. The third slide will come at the end of the next lecture on valence bond theory.